Hello everyone, myself Neeraj Kumar Gaud, Assistant Professor, BC Department, IIMT College of Management. Today, I am going to give an online lecture on limit and continuity. Let's start. Up to now, you have used algebra and geometry to solve problems where the things are basically staying the same or changing at the same rate. Calculus is a branch of mathematics that deals with things that are changing. One of the most basic and the fundamental idea of calculus is limits. Limit allow us to look at what happened in a very small region around the world. So we have two examples. One is the rate of change at any point on a curve. Another is acceleration of a rocket ship that is changing every part of a second. Now the first is limits. The roadmap will be limits, algebra of limits, and method to solve limits. That is, a limit is the value that a function approaches as the input approaches a certain value. So, from the given graph, if x approaches to a gives fx tends to a, then it is represented by limit x tends to a fx equal to l. So L is the limiting value of fx at x equal to a. X tends to a means that x approaches to a, that is x not equal to a. Meaning of limit x tends to a negative fx. This implies that x tends to a negative left neighborhood of a. It is also known as left-hand limit. In short, we use LH. Meaning of limit x tends to a plus fx. This implies that x tends to a plus right neighborhood of a. It is also known as right-hand limit. In short, we use RH. Meaning of limit x tends to a fx. This implies that x tends to a negative, a positive. So we have to look at both left and right neighborhoods. Let us understand the meaning of limit x tends to 2 negative fx and limit x tends to 2 positive fx. So from the given graph, in case of 2 negative, it means that x is approaching 2 on the number line from the left hand side. So minus 2 is in the left neighborhood. In the case of 2 positive, it means that x is approaching 2 on the number line from the right hand side. So 2 plus is in the right neighborhood. Now consider limit x tends to fx. RHL can be calculated by substituting x is equal to a plus h, where s tends to 0 positive. LHL can be calculated by substituting x is equal to a minus h, where s tends to 0. In simple word, LHL equal to limit x tends to a negative fx, which is equal to limit s tends to 0 f of a minus h. RHL with the limit s tends to a plus fx, which is equal to limit s tends to 0 f of a plus h. Limit of function exists if limit x tends to fx equal to limit of x tends to xa equal to L, which is finite value. Example, limit of a function fx is said to exist at x is equal to a when the left hand limit x tends to a minus fx equal to the right hand limit x tends to a plus fx equal to L, which is finite. So here the function fx is approaching to L1 from both the side of x is equal to a. Therefore, limit x tends to a fx equal to L1. Illustration, find out whether the limit exists or not at x is equal to 5, 13, 18 and 23.1. So from the graph, we check now solution. Limit x tends to 5 negative fx, which is not equal to limit x tends to 5 positive fx. This implies limit x tends to 5 fx does not exist. Limit x tends to 13 negative fx, which is equal to limit x tends to 13 positive fx, implies limit x tends to 13 fx exists. Next, limit x tends to 18 negative fx equal to limit x tends to 18 positive fx, implies limit x tends to 18 fx exists. Last, limit x tends to 23.5 negative fx, which is 5, and limit x tends to 23.5 positive fx, which is 7, implies limit x tends to 23.5 fx does not exist because LHL is not equal to RHL. Next example, so from the graph, limit x tends to a negative fx, the function is approaching to L1. Similarly, limit x tends to a positive fx, the function is approaches to L2, and L1, which is not equal to L2, implies limit x tends to a fx does not exist. Now point, if x is equal to a is the end point of the domain, then we cannot check LHL RHL point. In that case, we check LHL or RHL depending on the condition. Let's take an example. Limit x tends to 1 cos inverse x. So here the graph of cos inverse x. So the domain of cos inverse x is x belongs to closed interval -1 to 1. At x is equal to 1 plus h, where s tends to 0 positive, cos inverse x does not exist. So we only check LHL, not RHL. LHL equal to limit s tends to 0 positive, cos inverse 1 minus h, while putting h is equal to 0, so cos inverse 1 minus 0, which comes out cos inverse 1, which is 0. So limit x tends to 1, cos inverse x is 0. Now next is indeterminate forms. These are the expression whose values cannot be directly determined by substituting the values of x. So we have 7 indeterminate forms. They are as follows: 0 by 0, infinity upon infinity, infinity minus infinity, 0 into infinity, 0 to the power 0, infinity to the power 0, and 1 to the power. Whenever we talk about the indeterminate form, for example, 0 upon 0, it is not the exact 0 upon exact 0. It is tending to 0 upon tending to 0, or tends to 0 upon tends to 0. Similarly, 1 to the power infinity, it is not exact 1 to the power infinity. It is tending to 1 to the power infinity. That is, a limit we deals with approaching value, not the exact values. There are some forms which look like indeterminate, but actually they are determinate. Some of the examples are infinity into infinity tends to infinity, infinity plus infinity tends to infinity, a upon infinity, a is finite, is 0, infinity upon tends to 0, it tends to infinity, exact 0 upon tends to 0 is 0, x tends to 0 to the power infinity is 0, infinity to the power infinity is infinity, exact 0 to the power 0 positive is 0. Now we have illustration. We have 4 illustration. Number 1 is limit x tends to 1, x minus 1 upon x square minus 1. While putting the value x equal to 1, we get 0 by 0, which is indeterminate. Next, limit x tends to 0 positive, greatest integer x upon x, which is equal to limit s tends to 0, greatest integer 0 plus h upon h, which is equal to limit s tends to 0, 0 upon h, which is 0, which is determinate. Limit x tends to pi by 2, greatest integer x to the power 10x, which is equal to pi by 2, greatest integer 10 pi by 2, which is equal to greatest integer of 1.57 to the power infinity. The greatest integer value of 1.57 is 1, and 1 to the power infinity, which is 1, is called denominator. Last one, limit x tends to minus infinity, square root of x square minus 1, which is equal to square root of minus infinity square minus 1, minus of minus infinity square, which is tends to infinity, which is denominator. For the next illustration, if the limit n tends to infinity, n dot 3 to the power n upon n dot x minus 2 to the power n plus n dot 3 to the power n plus 1 plus 3 to the power n equal to 1 by 3, then find the possible values of x. Solution. So what we have to do, we have to take the common out 3 to the power n from the denominator. So we get it, limit n to the power infinity n dot 3 to the power n upon n dot 3 to the power n, open bracket, x minus 2 to the power n upon 3 to the power n plus 3 plus 1 by n, close open bracket, equal to 1 by 3. So we cancel out n dot 3 to the power n from numerator and denominator. We left with limit n to the power infinity 1 upon x minus 2 to the power n upon 3 to the power n plus 3 plus 1 by n equal to 1 by 3. Now for the limit n tends to infinity, we get limit n to the power infinity x minus 2 to the power n by 3, which tends to 0, provided x minus 2 by 3 modulus should be less than 1. That is mod of x minus 2 upon 3 less than 1. That is mod of x minus 2 less than 3. That is x belongs to open interval minus 1, 5. Not point. Any number in between minus 1 and 1 to the power infinity is 0. Any number greater than 1 to the power infinity is infinity. Exact 1 to the power infinity is 1. E to the power infinity tends to infinity. E to the power minus infinity, which is 1 upon e to the power infinity, which tends to 0. That is limit x tends to infinity, a to the power x will be 0 if a lies between minus 1 and 1, infinity when a is greater than 1, 1 is. The summary sheet of the limit will be a is limit is a value that a function approaches as the input approaches a certain value. We have 7 indeterminate form. They are as follows: 0 by 0, infinity upon infinity, infinity minus infinity, 0 into infinity, 1 to the power infinity, 0 to the power 0, infinity to the power 0. Limit x tends to infinity, a to the power x will be 0, infinity 1, when a lies between minus 1 and 1 will be 0, infinity when a is greater than 1, 1 when a is equal to 1. Now we have continuity of a function. Continuity in mathematics is a property of a function that allow us to study how they change and behave without any sudden jump or breaks. Continuity is essential for calculus, which deals with limit, derivative, integral, and infinite series. The roadmap will be continuity of function, then the definition of left and right continuity, then the condition for the discontinuity of a function, then the illustration for checking continuity of a given function. The first is continuity of a function. While drawing graph, if we do not need to pick up pen, then it is a continuous graph. And if we need to pick up pen, then it is a discontinuous graph. So we have a continuous function as well as discontinuous function on the screen. Continuity at the interior point. A function f(x) is said to be continuous at x equal to a if limit x tends to a positive f(x) equal to limit x tends to a negative f(x) equal to f of a, which is equal to a finite quantity, a finite value. Or f of a minus h equal to f of a plus h equal to f of a, where s tends to 0 positive, tends to LHF equal to RHF equal to value of function against. The type 3 is a limit x tends to a f(x) equal to f. Continuity at a boundary point. Consider a function y is equal to f(x) in an interval, closed interval a, where a is the left boundary and b is the right boundary. A function y is equal to fx is said to be continuous at x equal to a, that is left boundary, if f of a equal to limit x tends to a positive fx equal to a finite quantity. At x is equal to a, where there is no requirement to find LHL for checking continuity because a minus doesn't belong to closed interval a comma b. A function y is equal to fx is said to be continuous at x equal to b, right boundary, if f of b equal to limit x tends to b minus fx equal to finite quantity. At x equal to b, we cannot discuss RHL for checking continuity because b plus doesn't belong to closed interval a comma b. A function y is equal to fx is said to be continuous at x is equal to m interior point if f of m minus h equal to f of m equal to f of m plus h equal to a finite quantity where s tends to 0 positive. So let's take two example. First example, check the continuity of fx at x equal to a. So from the graph, it is clearly that there is no breaking point, no jump. So from the graph, s tends to 0 positive, f of a plus h, which is equivalent to f of a minus n, which is equal to the functional value at a, which is l. Therefore, fx is continuous at x equal to a. From the second graph, here x belongs to closed interval a to infinity. So x is equal to a is a left boundary. So from the graph, s tends to 0 positive, f of a plus h equal to f of a equal to l. Therefore, fx is continuous at x equal to a. Another example, check the continuity of fx at x is equal to a. So from the graph, when the s tends to 0 positive, f of a plus h, the value is m, and also the functional value at a is also m. But from the left side, that is when s tends to 0 positive, f of a minus h, the value is l. Clearly, m is not equal to l, therefore function is discontinuous at x equal to a. And we can clearly see it's a jump in a function. Now, we are going to check continuity of function fx at x is equal to b. So from the graph, x belongs to closed interval b to open infinity. So b is a left boundary. So f of b equal to n, f of b plus, which is equal to l. So f of b plus, which is not equal to f of b, if a function is discontinuous at x equal to b. Left continuous and the right continuous. A function fx is said to be left continuous at x equal to a if the limit s tends to 0 positive, f of a minus h equal to f of a, and if limit s tends to 0 positive, f of a minus h equal to f of a, but not equal to limit s tends to 0 positive, f of a plus h, then the function is discontinuous at x equal to a, but the left continuous at x. A function fx is right continuous at x equal to a if the limit s tends to 0 positive, f of a plus h equal to f of a. If the limit s tends to 0 positive, f of a plus h equal to f of a, not equal to limit s tends to 0 positive, f of a minus h, then fx is discontinuous at x equal to a, but the right continuous at x equal to a. Types of continuity problem. Three types of question in checking. Type 1, not equal type. Example, fx equal to x square minus a square upon x minus a when x not equal to a, 2a when x equal to a. Type 2, subjective type. If fx equal to x square minus a square x minus a when x not equal to a is continuous at x equal to a, then find f of a. Condition for checking continuity of type 1 and type 2 is limit x tends to a fx equal to the functional value. Type 3 is less than, greater than, not equal to. That is example, if fx is equal to x square minus a square upon x minus a when x less than a, 2a when x greater than a. Check the continuity at x equal to. Condition for checking continuity of type 3 is limit x tends to a positive fx is equal to limit x tends to a negative fx, which is equal to the function value. When a function fx contains greatest integer, fractional part, modulus, or 1 by x, then check LHL and RHL. If function is discontinuous at x is equal to a, if f of a equal to f of a plus not equal to f of a, that is, functional value is equal to the right hand limit but not equal to left hand limit. Similarly, f of a is equal to f of a minus not equal to f of a plus. It is functional value equal to left hand limit but not equal to right hand. Third, when f of a is not equal to f of a minus not equal to f of a plus, that is functional value is not equal to left hand limit not equal to right hand. Next is f of a plus equal to f of a minus, but f of a does not exist. That is left hand limit equal to right hand limit, but the functional value does not exist. The last one, f of a is not equal to f of a minus equal to f of a plus. That is functional value is not equal to left hand limit as well as right hand limit. So that's an example. That here f of a plus equal to f of a minus, that is left hand limit and the right hand limit both are equal, but f of a does not exist. So fx is discontinuous at x equal to a, because at a we have open. Let's take an illustration. Fx is equal to x upon greatest integer of x when x not equal to 0, 0 when x equal to 0, and check the continuity at x equal to 0. Solution LHL. Let x is equal to 0 minus h, where s tends to 0 positive, implies limit s tends to 0 positive minus h upon greatest integer 0 minus h. And we know the value of greatest integer 0 minus h minus 1. So we get limit s tends to 0 positive minus h upon minus 1, which comes out to be 0. Therefore, LHL, which is 0. And also the function value at 0 is 0. Now RHL, for y is equal to x upon greatest integer of x, this implies greatest integer of x is not equal to 0. This implies x doesn't belongs to closed interval 0, 1. So x equal to 0 positive is not in the domain. So we cannot discuss RHL for the limit x tends to 0 positive fx equal to f0, which is 0. Therefore, function is continuous at x equal to 0. Take another example. Fx is equal to e to the power 1 upon x upon 1 plus e to the power 1 upon x when x not equal to 0, 0 when x equal to 0. Then check the continuity at x equal to 0. Solution, left hand limit, let x is equal to 0 minus h, where s tends to 0 positive, equal to limit s tends to 0 positive, e to the power 1 upon minus h upon 1 plus e to the power 1 minus h, which comes out to 0 upon 1 plus 0, which is comes out to 0 upon 1, which is 0. Right hand limit, let x is equal to 0 plus h, comma s tends to 0 positive, equal to the limit s tends to 0 positive, e to the power 1 upon h upon 1 plus e to the power 1 upon h, equal to limit s tends to 0 positive, e to the power 1 upon h upon, we take the from the denominator e to the power 1 by h common out, we left with 1 upon e to the power 1 upon h, with change in e to the power minus 1 upon h plus 1. And it comes out 1 upon 0 plus 1. We left with 1 by 1, which is 1. So here the left hand limit is 0 and right hand limit is 1. Therefore, function is discontinuous at x equal to 0. Another example, fx is equal to x plus 1 when x less than equal to 1, 2x minus 1 when x is greater than 1. And they check the quantity at x equal to 1. So from the graph, we can easily check out. Also, mathematically, we can check LHL, let x is equal to 1 minus h, where s tending to 0 positive. Limit s tends to 0 positive 1 minus h plus 1, which is 2. So RHL, limit x tends to 1 plus h, s tending to 0 positive. Limit x tends to 0 positive to 1 plus h minus 1, which is equal to 1. Therefore, RHL is 1. So f of 1 will be 1 plus 1, which is 2. So f of 1 minus h equal to f of 1, but not equal to f of 1 plus h. If a function is continuous and x equal to 1. Point function. Any function which has only one point in its domain is a point function. Fx is equal to under root of x minus 1 plus under root 1 minus 1 exists for x equal to 1 only. For domain, x minus 1 greater than equal to 0 and 1 minus x greater than equal to 0. Intersection of above cases implies x is equal to 1 and range y is equal to 0. Another example, fx is equal to square root of x plus square root of minus x plus 2 for domain x greater than equal to 0 and minus x greater than equal to 0. Intersection of above cases implies x is equal to 0 and range y is equal to 2. Continuity of a point function. A point function is a discrete function and is said to be continuous in its domain. Here we do not check f of a minus h equal to f of a equal to f of a plus h. Continuity of modulus function. If y is equal to fx is continuous at x equal to a, then y is equal to mod x is also continuous at x equal to a. Example, since y is equal to sin x is continuous, implies y is equal to mod sin x is also continuous. Remark, continuity is only meaningful when it is checked in the domain of a function. Example, let's check the continuity of y is equal to log x. So check the continuity at x equal to 0. Here the question is meaningless because as the domain of y is equal to log x is open interval 0 to infinity, because 0 is not the part of domain. Check the discontinuity x equal to minus 1. Here the question is meaningless as the domain of y is equal to log x is open 0 to infinity, because minus 1 is not in between 0 and infinity. Continuity of inverse function. If f is strictly increasing continuous function in closed interval a comma b, where f of a is c and f of b is d, then f inverse will also be strictly increasing continuous function in closed interval c comma d. Take an example. Take fx is equal to e to the power x when x less than 0, x square plus 1 and x greater than equal to 0. Check the continuity of f inverse. So let's plot the graph of f inverse x by taking mirror image of fx about y is equal to x. So we can see that f inverse is continuous in the domain. Continuity in interval. Continuity in open interval. A function f is said to be continuous in open interval a comma b if it is continuous at every point between x is equal to a and x is equal to b. All elementary functions are continuous in interval where they are defined. For example, fx is equal to sin x upon 1 minus cos x. Check the continuity at x equal to pi by 3. Cos x, which is not equal to 1, implies x not equal to 2 and pi and belongs to integer. X is equal to pi by 3, which doesn't belongs to 2 and pi, comma, and belongs to integer. Therefore, fx is continuous at x is equal to pi by pi. For example, fx is equal to tan x. Check the continuity in its domain. Domain of tan x is x belongs to r minus 2n plus 1 pi by 2 and belongs to integer. Within the domain, tan x is continuous, but in x belongs to r, tan x is discontinuous as the function is great at every 2n plus 1 pi by 2. Continuity in a closed interval. A function f is said to be continuous in closed interval a b if f is continuous in open interval. F is right continuous at x is equal to a. Limit x tends to a positive. Fx is equal to f of a equal to finite quantity. F is left continuous at x equal to b. Limit x tends to b minus fx equal to f of b equal to finite. Which of the following option is not correct? Fx is continuous in closed interval 2, 5. Fx is continuous in closed interval 2, open interval 5. Fx is continuous in open interval 2, 5. So first we are going to check the functional value at 5. We know the functional value at 5 is 4. And the left-hand value at 5 is 5. So fx is discontinuous at x equal to 5. Now at x equal to 2, f of 2 is 2 and f of 2 plus is also 2. So function is continuous at x equal to 2. Therefore, the function is continuous, close interval 2, open 5. So option B and C are correct answer. Now the summary sheet. A function fx is said to be continuous at x is equal to a if h tends to 0 positive, implies f of a minus h equal to f of a plus h equal to f of a. That is LHL equal to RHL equal to the value of function at x equal to. A function y is equal to fx and x belongs to closed interval a is said to be continuous at x is equal to a. Left boundary if f of a equal to limit x tends to a plus fx equal to finite quantity. If function y is equal to fx, x belongs to closed interval a b said to be continuous at x equal to b, right boundary. If f of b is equal to limit x tends to b minus fx equal to a finite quantity. A function fx is left continuous at x equal to a if f of a minus equal to f of a. A function fx is right continuous at x equal to a if f of a plus equal to f of a. A function is discontinuous at x equal to a if f of a equal to f of a plus not equal to f of a minus, f of a equal to f of a minus not equal to f of a plus, f of a not equal to f of a minus not equal to f of a plus, f of a plus equal to f of a minus but f of a does not exist, or f of a is not equal to f of a minus equal to f of a plus. Any function which has only one point in its domain is a point function. A point function is a discrete function and is said to be continuous in its domain. If y is equal to fx is continuous at x equal to a, then y is equal to mod x is also continuous at x equal to a. Continuity is only meaningful when it is checked in the domain of a function. Inverse of a discontinuous function can be a continuous function. A function f is said to be continuous in open interval if it is continuous at every point between x equal to a and x equal to b. A function f is said to be continuous in a closed interval if fx is continuous in open interval a comma b. A limit x tends to a plus fx is equal to f of a equal to a finite quantity. A limit x tends to b minus f of x equal to f of b, a finite quantity. Thank you, everyone.